Hello students, welcome to EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about a module entitled Crystal Structure and Space Groups from the paper Mathematical Physics. So let us see what we are going to learn in this module. In this module, we will learn about the space groups which are relevant in solid state physics. We will learn in particular how Bloch's theorem, an important theorem in the study of electronic structure of solids, arises out of symmetry considerations alone. We will see that a crystal can be thought of as formed of a lattice and a basis. Lattice is a regular pattern of points in space. It can, for our consideration, we will consider a lattice to a regular pattern in three-dimensional space in which a neighborhood of a point is identical to any other point. The crystal consists of lattice, which is a regular pattern of points, and any other point, neighboring point is identical to this, and the basis consists of a group of atoms, molecules or ions associated with each lattice point. A unit cell is an important concept, is a basic repeated unit and is specified by three lengths A, B, C and three angles alpha, beta, gamma in three dimensions, and this unit cell forms a building block of the crystal. So let's discuss the space groups. Consider a three-dimensional lattice generated by three primitive translation vectors A, B and C with the boundary conditions given by the vector R minus n1 times the vector A is equal to R itself, and vector R minus n2b is equal to the vector R minus n3c is equal to vector R, where R is the position of the point in the lattice. So in this way, you can see that the total number of primitive cells in the lattice is capital N is equal to N1 into N2 into N3. Notice that N1, N2, N3 are integers, and each primitive cell has a volume given by the triple scalar product A dot B cross C. Now we define a translation operator T as a function of these integers n1, n2, n3. So T n1, n2, n3 denotes a translation through given by vector T is equal to n1a plus n2b plus n3c. Thus, the translation operator T acting on the vector R translates the vector R to R plus a vector given by n1a plus n2b plus n3c, which can be written as R plus the translation vector T, which is a function of n1, n2, n3. That is, a translation of operator T acting on R takes it to a vector which is R plus the translation vector T. It is easy to see that translation forms a group. Then what is the identity operator of this group? Obviously, the identity operator of the group E is given by T, where all the three integers n1, n2, n3 are 0. And the product of two translation operators, say T, a function of n1, n2, n3, and another T function of m1, m2, m3 operating on the vector R, takes it to translation operator which is given by T, a function of n1 plus m1, n2 plus m2, and n3 plus m3 acting on R. That is, the effect of two successive translations is equal to a single translation where n1, n2, n3, m1, m2, m3 are placed by n1 plus m1, n2 plus m2, n3 plus m3 respectively. Now, obviously, this constitutes an abelian group. And what is the order of this group? The order of this group is capital N1 into N2 into N3. And since it's an abelian group, all its irreducible representations are of order 1. So an actual three-dimensional lattice, what symmetries will it have? It will be invariant under the point group transformation, for example. But the lattice has a further property of being invariant under translation. Thus, the symmetry operation, which we write here as R, a function of the vector R, on a crystal will take the vector R to another vector R prime, such that this R prime is obtained by a rotation of the vector R plus a translation. That is, the vector R prime is equal to the symmetry operation R acting on the vector R, which is equivalent to A acting on the point symmetry operation acting on the R plus a translation by a vector T. And this symmetry operator or element is denoted by A comma T. So A stands for the point group symmetry and T for the translation. In the case of complex crystals with more than one atom per primitive cell, it may happen that the crystal may not be invariant under a point group operation. This is very interesting, that the molecule is invariant under the point group operation, but the crystal may not be. Particularly if you have a crystal which have more than one atom in a primitive cell, or it may not be invariant under translation individually. So individually the translation as well as the point group symmetry operation may not be symmetry of the crystal, but these two operations together may be. So the combined operation followed by a translation may still leave the crystal invariant. Now let us consider a one-dimensional lattice with a lattice constant A, and let's consider a lattice which is a complex lattice in the sense that it has two atoms per primitive cell. Each lattice point is denoted by a dot and is associated with two atoms which are denoted by a full circle and a circle with a dot in between. You can see the slide. It's not a very good slide, but it will explain the essential feature. Now, if I translate by A by 2, then you can see that because of the fact that this is a complex crystal system which have two atoms per primitive cell, the translation by A by 2 is not a symmetry of the crystal. It changes the symmetry. If I follow this translation by A by 2 with the rotation of pi about the axis passing through the lattice points, which is perpendicular to the lattice axis as shown below, then I get back the symmetry, and the symmetry is restored. Such a symmetry, which consists of two operations, a translation by A by 2 and then a rotation, is called a screw rotation. The symmetry under a screw rotation is thus defined by the following operations. Number 1, a clockwise n-fold rotation about an axis, and number 2, a translation along the axis, expressed in fraction of a lattice translation parallel to the axis, then this is called the screw axis. Another symmetry in an ideal crystal is the so-called glide plane symmetry. The glide plane symmetry operation consists of reflection in a plane followed by a translation through a vector in the plane. So, if the symmetry of the crystal is such that the symmetry is restored after a reflection in the plane followed by a translation through a vector in the plane. Glide plane symmetry is not applicable to chiral molecules. These two operations constituting glide plane as well as screw axis commute with each other. The full symmetry group is now called the space group. What are the elements of this space group? The elements of these space groups are combination of group and translation group elements. Its operation is denoted by A and T, and its effect on the position vector is that this symmetry operation AT acting on R rotates R through a rotational matrix X plus translated by a vector T. The successive operation of the two such elements, that is, an element A with the translation T1 and the element B with the translation T2 on R is given by BT2 and AT1 acting on R, means that first AT1 acts on R, so this is equal to BT2. AT1 acting on R takes R to AR plus T1. Then BT1 acts on this vector AR plus T1. Therefore, it takes it to BAR plus BT1 plus T2, which means that the group multiplication of these two symmetry operations, BT2 and AT1, is equivalent to a symmetry operation BA, comma, BT1 plus T2. So this is the group multiplication for the symmetry operation. The identity and inverse elements of the space group A and T are given by, identity is obviously represented as E, which has the element E, rotation and no translation. And the inverse of this space group element AT1 inverse is equal to the inverse of A and the negative of A inverse acting on T respectively. I should mention at this stage, as a curiosity, that there are a total number of 230 different space groups discovered in the 19th century. The successive operation of two elements which we have seen, the two elements of the space symmetry being AT1 and BT2 on R, is given by BT2 and AT1 is equivalent to an operation BA and a translation BT1 plus T2. This can be seen as follows. The symmetry operation AT1 acting on R takes it to AR plus T1. Then BT2, the symmetry operation BT2 acting on this AT1R is equal to BT2 symmetry operation acting on A and R plus T1, which takes it to BAR plus B T1 plus T2, which is equivalent to the symmetry operation BA and the translation operator B T1 plus T2. An example can be seen as follows. The inverse element of the space group AT is given by A inverse and a translation which is minus A inverse T. See, AT, operation AT multiplied by the operation A inverse minus A inverse T acting on R is equal to the, by definition of group multiplication given above, is equal to A inverse, comma, minus A1 T acting on AT R, which is equal to A inverse, comma, minus A1 T acting on AR plus T, which is equal to A inverse AR plus A1 T minus A inverse T, which is equal to A inverse AR, which is equal to R. Therefore, this is the inverse element. So, inverse element of the space group AT is given by A inverse, comma, minus A inverse T. So, in 3 dimensions, there are 14 Bravia lattices and they are divided into 7 systems. The 7 systems with their point groups and translation symmetry, which is completely determined by the type to which they belong, they are all shown in the table and I have discussed them. It should be remarked that if A, T is an element of the space group, it does not necessarily follows that A, 0 is also an element of the space group. That means A, T is an element which consists of a translation and a symmetry operation A. If this is an element of the space group, it does not follow that A alone with no translation is also an element of the space group. In other words, A0 is not necessarily a symmetry operation of the crystal. As we have seen above, during our discussion of a screw axis and glide planes, because in the case of, we discussed earlier, we saw that if we don't follow a rotation by a translation, then in complex crystals, for example, is no longer a symmetry. So this means that A alone, with no translation, is not necessarily a symmetry operation of the crystal. So to summarize, at this stage we can say a point group describes the symmetry of molecules, whereas a lattice has translational symmetry. Combination of the point group and lattice symmetries constitute what are known as space group symmetry. A space group is the complete description of an ideal crystal, which of course is considered here as an infinite crystal. We will now discuss an important theorem which arises from the consideration of symmetry operations in crystal, and the famous theorem you are already familiar with from your quantum mechanics and solid state physics papers is the famous Bloch theorem. Consider an electron in a crystal. The energy and wave function of an electron in a crystal are obtained by solving the Schrodinger equation H psi r is equal to, what is H? H is the Hamiltonian, which is the kinetic energy plus the potential energy, which is minus h square by 2m del square plus v of r. Operating on psi r is equal to E psi r. Here Vr is the potential experienced by the electron in the lattice. And the lattice, of course, is periodic. E is the eigenvalue for the Hamiltonian H. Psi r is the corresponding eigenfunction. Full symmetry group of the Hamiltonian is the space group of the crystal under consideration. Because crystal has a symmetry which is given by the space group, and the full symmetry group of the Hamiltonian is then the space group of the crystal under consideration. The electron in the crystal can be considered as moving in a periodic potential formed by the nuclei or the ions fixed in their lattice sites. The nuclei and the ions can be considered as fixed because of their mass, which is thousands of times greater than the electron mass. The motion of the nuclei, including oscillations and vibrations of the nuclei, are therefore can be assumed to be absent because of their heavy mass compared to the mass of electron, and the interelectronic forces are also assumed to be absent. So in effect, what we have that the electrons form a free electron gas, and in such a situation, the electrons are moving in some kind of an effective periodic potential, which is the potential obtained by the interaction of the electron with the ions. In such a situation, electron energy and wave functions are obtained by solving the above Schrodinger equation. The Hamiltonian H is obviously invariant under the full space group of the crystal, in particular under translation. The translation operator, as defined above, T, n1, n2, n3, denotes a translation through a vector R, capital R, given by n1a plus n2b plus n3c. The potential Vr is periodic with the periodicity of the lattice, which is the translation through the vector capital R. That means V at a point R is equal to the potential when you translate R to R plus capital R. So Vr plus R is equal to Vr. Since HR is invariant under translation group, it commutes with the translation symmetry operator, TR. Thus, the commutator of H and TR, that is H, TR, is equal to 0. Now, if psi n is an eigenfunction of H with eigenvalue En, then we know that in that case, Tr psi n is also an eigenfunction of H with the same eigenvalue En because Tr commutes with H. Thus, psi n as well as Tr operating on psi n are degenerate eigenfunctions of H with the eigenvalue En. That is, H psi n is equal to En psi n, and H T psi n is equal to T H psi n because the commute is also equal to En T psi n, which means that psi n and T psi n are related. So we can write T of R operating on psi n is some scalar function of R multiplied by psi n. That is, Tr psi n is equal to C of R, psi n with C of R is some scalar function. So Tr acting on psi n R, Tr is a translation operator which translates the position vector by an amount capital R. So Tr acting on the wave function psi n R gives us a wave function psi n at the point R plus capital R, which is equal to a scalar function C of R into psi n from what we have seen above. Therefore, Tr prime acting on psi n is equal to Tr acting on psi n at R plus R because Tr prime acting on psi n translates R to R plus R prime, which is then equal to psi n R plus capital R plus capital R prime. Which means that the scalar function is such that the product of the scalar function evaluated at R and R prime, that is C of R into C of R prime, is equal to C of R prime into C of R, which is equal to C of R plus R prime. That the product of these two scalar functions at the positions R and R prime is equal to this scalar function evaluated at the point R plus R prime, which means clearly that the scalar function C of R must be of the exponential type such that its product, if you take the product of it, the exponents get summed. So CR then can be written as exponential I k dot R. Therefore, the wave function, Schrodinger wave function for the motion of electron in a periodic lattice can be written as psi as a function of two quantum numbers n and k. The psi n k, a function of R, is equal to e to the power I k dot R into a wave function u n k, a function of R alone. This can be satisfied if and only if psi n k R is equal to e to the power I k dot R u n k of R. The Bloch theorem is an important theorem. The Bloch theorem states that the eigenfunctions of the Hamiltonian of an electron in a periodic potential U of R such that U of R plus capital R is equal to U of R. That is, the potential has a periodicity capital R. Then Bloch's theorem says that the eigenfunction of the electron, of the Hamiltonian of the electron, must be of the form that psi n k of R is equal to e to the power I k dot R into u n k, which is a function of R, with the property that psi n k R plus capital R is equal to e to the power I k dot R psi n k R. That is e to the power I k dot R, capital R, acting on the wave function psi n k, which is evaluated at the vector R, gives us the vector eigenfunction evaluated at the point R plus capital R. In this, the vector k is called the wave vector of the electron in the state psi n k. The wave vector k is a good quantum number of the electron in the crystal as long as the translational symmetry of the Hamiltonian is not disturbed. K is not the momentum of the electron. Psi nkr is not the momentum eigenstate of the electron. Let's now consider the linear momentum operator. The linear momentum operator P in quantum mechanics is minus IH cross del. The linear momentum operator acting on the electron wave function now for an electron moving in the periodic potential by Bloch's theorem is psi nk of r. So this momentum operator P acting on psi nkr is equal to minus IH cross delta acting on e to the power I k dot r unk of r. So which can be written as IH cross e to the power I k dot r unkr minus IH cross e to the power I k dot r and the del operating on unk. That means that the momentum operator acting on the wave function sin nk projects out the momentum k, so is equal to minus h cross k psi n and is equal to this minus IH cross e to the power I k dot r, the del operator acting on u of nk. Now this h cross k is not the electron momentum, is called the crystal momentum. Then the Schrodinger equation h psi nk enk psi nk can be reduced to a Hermitian eigenvalue problem for an electron in a primitive cell of the crystal. How can it be done? It can be done by noting that Bloch's theorem psi nk r can be written as e to the power I k dot r unk r. Therefore, del square psi nk r is del of e to the power I k dot r unk, which can be expanded in this form. And finally, del square psi nk r can be written as e to the power I k dot r into ik plus del whole square unk r. Thus, the eigenvalue equation to be solved for enk and unk simplified, and the final equation that has to be solved becomes minus h cross square by 2m ik plus del whole square plus vr acting on the wave function unkr, which is equal to the eigenvalue enk into unkr. So essentially what has happened in all this is that the original equation h cross square by 2m del square is replaced by minus h cross square by 2m ik plus del whole square. So that's the change that has happened when you get the final eigenvalue equation for the motion of electron in a periodic lattice, with the boundary condition that unk at r plus capital R is equal to unk at r. The Bloch function psi nk r with the corresponding eigenvalue enk then determines the electronic band structure of the crystal. So we are in a position to summarize what we have learned in this module. The first thing is that a lattice has translational symmetry as opposed to a molecule which only has the point group symmetry. The combination of point group and lattice symmetries constitutes what is known as space group symmetry. The Bloch theorem is the theorem that tells us that the eigenfunctions of a Hamiltonian of an electron moving in the periodic potential u r plus capital R is equal to ur, that is with the period capital R, is of the form psi nk r can be written as e to the power I k dot r into unk of r, with the property that psi the wave function corresponding to the quantum number nk evaluated at r plus r is equal to e to the power I k dot r into the wave function evaluated at r.